So I hope you can all see my presentation. And as it has been already said, this will be a talk to convince you that Xarray is not just pandas in multiple dimensions, but a lot more. I'm currently piled higher and deeper at the Institute of Plasma Physics of the Czech Academy of Sciences, which hopefully explains why my relationship to data is that it is wrong. I'm not a core Xarray developer, but I'm a very active user, and I develop some of my own extensions and extensions that other people use. So this talk will be given mostly from a perspective of a very active user. I'll start by explaining why you might want to consider looking at yet another library when we already have NumPy and Pandas. Then I'll give you a brief overview of at least the basics of the Xarray API. I'll start with a brief technical structure overview and then give you some basic usage examples. And then I'll show some more advanced usage. For example, how you can wrap some nice methods from Scipy. And then one of my favorite, I would say perhaps abuses of the whole API to essentially write parallelized for loops with Dask and broadcasting magic. So we all love NumPy, but quite often we find ourselves in this situation where we have some dependent variable, here y, and we would want to select y for which x is between 2 and 3. One common workaround that I've seen used many times, and I've used it in the past myself, is that you create a Boolean mask. That works, but it's not exactly efficient. Now these days, it's a no-brainer. You just use pandas, and it works very well. It's very efficient and quite concise. But pandas is mostly oriented at 1D. You could say that data frames are 2D. That is kind of true, but most of the API is still aimed at working with data frames as if they were dictionaries of series. So it's not exactly general when you want to work with more than one dimension. You can actually get away with working with something like a multi-dimensional array if you flatten all the dimensions into one multi-index, which actually is pretty useful when your data is sparse in the multiple dimensions, but it's not exactly convenient and super easy to use. And this is where Xarray comes in, because it generalizes this pandas indexing machinery into multiple dimensions. But there's more. One other thing that I've often encountered is that I've wished that NumPy had named dimensions. And let's first think about what we actually mean by dimensions. When we work with NumPy, we're actually working with something we might call algebraic dimensions. That means rows, columns, and depths. But these may or may not correspond to some physical dimensions of let's say, spatial or temporal meaning. So let's say I have some tensor of shape 573, could correspond to time and some spatial dimensions. And let's say I then perform some calculations and I move around the axes for some reason. So I'm transposing it and I'm swapping axes, who knows what it is. Now, can you guess what the shape is? It's not that easy. And now let's say I want to perform the mean over the x-axis. And now where is it? It's not that easy to guess, actually. Now we have to think, well, I transpose it, so I reverse this order. Now I swap the second and third. So which one is it? Well, the correct answer is that it is the second one. You see that we removed the dimension with size 7, which was x. So that is something that is quite inconvenient. And what Xarray does is that it assigns names to dimensions. So instead of using axis equals something, you can specify the dimension to be some function be applied over directly by a name. Of course, that works in wrapped functions and methods, and we'll talk about those later. So you don't need to remember any explicit dimension ordering. And another benefit is that if some dimension is missing, then if you want to apply, let's say, a mean over that dimension, then you'll get a failure, an explicit failure. Whereas if you are using, let's say, mean with axis -1 or 0 or something like that, then that might actually work, but it suddenly might pack a surprise for later when down the line you might find out that, oh, my array is suddenly has a completely different shape than I expected. And in Pandas, a data frame has only algebraic dimensions. They call it the index and columns dimensions. With a multi-index, you kind of do have explicit dimension ordering because you can have dimension level names in the multi-index, but then you have to track their order and so on. And yet another thing that I love and probably makes NumPy and all the other libraries derived from it so popular and powerful, here I'm talking, for example, about TensorFlow or PyTorch or whatever, is that there is this thing called NumPy broadcasting, which, at least in terms of computation, means that you can perform implicit and with NumPy at the C level very fast for loops in arithmetic operations, and they vectorize automatically. Well, kind of automatically. And when you apply functions which support such APIs, mostly universal functions, their arguments also vectorize. But it's not exactly so easy and so readable in practice. So consider that I have this 1D array of time values, and it does have those. To make it simpler, I give it the same size that as the time dimension had in the previous arrays, and now I just want to multiply it with the previous result. But that fails spectacularly because NumPy broadcasting has some rules, and for instance, the dimensions have to align from the backwards in the shape. And so this doesn't actually work. So one solution is to reshape this. So you say, well, okay, I understand that I'll have to eat my pie and reshape it like so, and then it works. Now, tell me, would you just remember which way you have to reshape it? It's not that easy. And so this is again where Xarray comes to the help. It comes to the rescue because it handles all of this broadcasting according to dimension names, which it knows about. So it checks whether the dimension sizes match, and possibly it can align them by associated coordinates if they don't match completely. And it handles all this reshaping and transposing before arithmetic operations. And it also handles all of the broadcasting within ufuncs, or you can use it for other functions via the apply ufunc helper API, which I'll briefly show later. And just to be fair with Pandas, with a multi-index flat n-dimensional data frame, you kind of still get the same thing because you're aligning just a 1D thing, so there's no alignment actually. And just to point out that this really is a general problem. PyTorch, since version 1.3, has this thing called named tensors, which have a similar use case, that they track the dimensions according to their names. So enter Xarray. Let me say that this is actually a pure Python library, but it does depend on some compiled dependencies, some of them which are optional. Of course, it depends on NumPy and mostly on Pandas. And it's heavily inspired by the netcdf file format, so it makes a lot of use of that if you want to store data, but it's not mandatory. And it's a project with one of the best documentation websites I've ever seen. It's very well structured and has many examples. So it's whenever you actually want to learn something, how to do something with Xarray, you almost always find it there. And just to give a brief historical context, which will hopefully shine a bit of light why some things work they do. This is actually an evolution of some internal tool they've developed at some climate corporation group. So it has been mainly used and developed by people working with climate science or geoscience. Originally, they released it as Xarray, and they quickly realized that this is not exactly a good name, because of course it clashes with many packages used by other people. And a few years ago, it also became part of the NumFOCUS group. So I'll first start with the technical overview. Now there's this thing called a variable object, it's actually an internal part of the API, but it's the core building block. So you don't actually need to use it, and you don't really need to know much about it in day-to-day usage of Xarray, but I believe it's very useful to know about it in order to appreciate what Xarray actually does. So this object wraps a NumPy array, or at least not a NumPy-like array. It actually has to be something called a duck array, so it just has to fulfill some behavior that a NumPy array would have. And you wrap that with some dimensions metadata, and possibly some other optional metadata. So it's not an ND array subclass, but it has many sort of mixin properties. So it has all of these various attributes and methods that you might expect from an ND array-like class. And that's a very important point to make, that Xarray is built on the idea of composition over inheritance. So they don't actually make subclasses of ND arrays, they just put together many mixin classes, and that's how they add in various properties. And it's heavily inspired by this netcdf file format. That stands for Network Common Data Format. Since version 4, that essentially means it's the hierarchical data format plus some geoscience data conventions. So typically you import Xarray as XR, as you might do with NumPy as an NP. And now we just wrap some random NumPy array. And all we do is that we specify the names that correspond to these algebraic dimensions. These are just names. They could be anything, just strings. And we can also specify some arbitrary metadata, which is useful to have, especially when you're working with simulation data, possibly some encoding metadata when you're working with some special input-output backends, but it's not mandatory. And this is the result. You see that they already have their own HTML representation in Jupyter Notebook. So you see that it essentially just wraps this NumPy array, but it has this metadata, which tells us the names and order of the dimensions. And all of the further API that I will cover in a moment, mainly data array and dataset. These are containers which are essentially built on top of mappings, which point from some name of a variable to a variable-like object. When I'm talking about, I'll be talking about mappings. For those of you who don't really know or aren't familiar with that term in Python, that essentially just means I'm talking about objects which behave like dictionaries. So the data array container is essentially mostly like a variable, but it's got associated coordinates. So it wraps one main array, and we can possibly give it some specific name. And the new thing is that we add coordinates attribute, which is a mapping from a coordinate name to some associated coordinate or label data array. So this is how we would create a data array. Again, we've got some data, a NumPy data. We have to tell what are the names of these algebraic dimensions. We can give it a name. And then we specify a dictionary or a mapping of these coordinate arrays. You see that I don't have to be actually data arrays when I'm constructing it. It wraps it automatically. Typically, you'll want to provide coordinate labels which correspond to some dimensions, but it's not mandatory. And here we have some extra data. So this is the result. Looks similar as before, but now we got this coordinates mapping here. You see that this HTML representation has nice collapsible features and so on. And what happens when we add these coordinates, which whose name corresponds to some dimension in this data array, and if it's 1D, then it creates a pandas index for that dimension. So here we see that this T coordinate indeed is present. And because we also specify the X coordinate, we have an index present, which we can then use for indexing and slicing and so on. So just to note this representation in Jupyter Notebook, it's HTML by default since a recent version. And you might have noticed that some of these dimensions are bold and some aren't. That's because a bold dimension tells you that it does have an index associated, so you can use it for slicing, label-based slicing. If it doesn't have a bold name, then it probably doesn't have it available. And here I added an extra coordinate, which isn't associated with any dimension, and you see that it is present, but it's not bold. When you see it in text form, you don't have bold in text form. So instead, an asterisk symbol is used in front of the coordinate name in the coordinates mapping. And those dimensions without coordinates are explicitly listed. So at this point, I think it's useful to point out that whereas in Pandas, the core building block of everything is an index, and its presence is essentially mandatory. Even if you don't supply an index, you get sort of a placeholder integer index. In Xarray, the real core building block are the dimensions, which are encoded in a variable-like object. And the index is actually optional. So that's a big difference. And now the data set is essentially just a container, which is essentially just a mapping of data arrays. So it's similar to how a data frame is essentially a mapping of series in Pandas. And the main point is that it actually contains just one chords mapping, which is a union of all the contained variables of the coordinates of all the other contained variables. So we might define a data set like so, that we will, these will be the data variables. We'll give them some dimension. We'll say what the dimension names are and supply the data. And we might have a different one here with only some dimensions and perhaps some different data. I'm just using part of the data. And we'll supply coordinates which are shared by all of the data variables. And here's the output. So it's a data set. We're told that it has these dimensions, it's got these coordinates and these data variables. So data variables is a mapping, again, similar to chords from name to data array. And this is the mapping that is actually used whenever you apply any mapping like API to the actual data set. So the data set is a mapping itself. It does support its API, so you can use item getting or assignment. You can use the keys method, items method, iterate over it. As of this version, it operates on this only on this mapping. Previously, it operated on the variables mapping, which was a union of both chords and data variables, which would return something different. So when it's safer to explicitly say over which mapping you want to, let's say, iterate or something like that, if you ever encounter that. And you might be wondering, so what's the actual difference between this coordinates mapping and this data vars mapping? To some extent, it's mostly semantic. This coordinates mapping is intended mostly for fixed or independent quantities, and the data vars are intended for measured or dependent quantities. It's also inspired by the netcdf file format, where there's this distinction, and usually it's quite a reasonable distinction. Of course, there's a big difference in its usage for indexing. Only those variables in chords can be used for indexing if they're 1D. And a lot of various helpers or other libraries might assume that this is true. For instance, the plot accessor, which we'll cover later, will take X or values or labels from this mapping, and the Y from this mapping, or in the case of 2D, the XY from this one, and the color, let's say, from this mapping. So that's the main difference. So for this tutorial, I'll load one of the tutorial data sets provided by Xarray. It's air temperature data above the US in some 2 years. I'm not a climate scientist, so here's a big fat disclaimer. All of this is just for illustration, and don't make any conclusions from whatever I do with the data, and hopefully I won't be doing anything too stupid. So that's that. So let's load it. If you run it on your own later on, this just downloads and caches some 17 megabyte netcdf file and wraps it and opens it with the xropen dataset function. So here we have another data set. It's a bit larger than we had last time. So finally something to work with. And one thing you might notice is that we only see 3 dots here for the data. So we look at the data and there is no data. It just tells us that it has a lot of values of this data type. Why is that? Well, that's because open dataset, and there's also a similar method called open data array, actually don't load all of the data into memory at the beginning. They only load coordinates into memory. And of course, they inspect the file and find out what variables are available. But that means that selecting and slicing still works, but even with index. And the data variables are loaded only when their actual values are truly accessed. That means when you try to calculate something or you try to slice them, or you can do it explicitly with the load method. There's also a companion method called load dataset, which just follows open dataset with load. So it will load all data into memory, but that's typically not what you want to do, although for some other operations you might. So it just gives you some control. So if we then access this data array, this air temperature data array, and we pluck it out of the data set, then we see it tells us it's just got these many values of this data type. But now if we try to slice it, or well, we are actually slicing here because as you might have noticed, this is actually a date time array. So it works in a similar way as in Pandas. If you supply just part of the date, you'll actually create a slice over some time period. Then it actually loads actual data. And you see that it actually loads 4 time slices because this doesn't specify the hour. One thing that we love in Pandas is that you have these attribute access aliases, and it works in a similar fashion in Xarray as well. So if you access ds dot some name, then it first tries to access it by item name, which then for data set means it first tries the data vars, and if it's not there, it tries the coordinates. And if it's not there, then it tries if it might be an attribute name. So all of these things will return pretty much the same thing, but there's a catch. These two things don't, the attribute access and item access may not return the identical object because these data arrays which are returned are created on demand. So these objects will not be identical, but they will be considered equal in terms of dimensions and content. So you see that you can access whatever you want in a very straightforward way. And of course, you have to make sure that you're not aliasing some other methods. For data array, it looks in a similar way. There's the difference that it doesn't have data vars because itself has just one data variable. But surprisingly, you can actually access a coordinates variable from a data array by item method, by the getItem method. But that's sort of just a quirk. Okay. Of course, part of why we like attribute access is because we like tab competition, and Xarray does have some mixing classes which implement this helper method, which is recognized by Jupyter and other, and possibly some other competition libraries. And if you use attribute style access, then if I start writing A and I press tab, then you'll see that I get the air variable suggested, but I also get a lot of these various methods, which I might or might not want to find. So in that case, the item style access is sometimes a bit more convenient because it will obviously find only those variables which are actually members of the data set, though it also finds some Jupyter mess. I'm not sure if that's my bug, just bug in my setup, or if it's just a Jupyter issue. On the other hand, the attribute style access does have better change tab competition. Of course, that depends on how your tab competition library works. For example, if I type air and I type air all, then that works, whereas this probably won't work. It actually works sometimes, but it's a bit slower because it has to obtain the object and so on. So now let's get into more sort of use cases. So when you have a data array, it does kind of feel like a NumPy-like array. and that also is true for a variable object. The underlying data are actually properties, and you can either use the data or values properties. The data is whatever is truly contained by this object. It might be an ND array, or it could be a lazy data wrapper, or a Dask array, or a sparse array. But when you use the values property, you always get an ND array. It kind of calls NumPy as array on data. So when you want to apply a function to some data, it's usually safer to use this. So if we have some data array which is wrapping an ND array, then these things will probably be the same. But in this case, they aren't, because it's not all of it is actually loaded into memory. And it does have all the various ND array-like attributes like ndim, shape, size, and bytes, d type, whatever. And there's two extra, which are important. That's the dimension names and order, and also a mapping from their names to the sizes of each dimension. So it's kind of a better form of shape. This is probably will be ordered the same way as dims in Python 3, but it's not exactly guaranteed. Okay. So now finally we get to how we index and select data when we do know the order of dimensions. So of course it still works like a normal array, so you can use integer positional indexing, and you can also use label-based indexing as you would do in Pandas. And of course, as with Pandas, because we are using Pandas indices, label-based slicing is end inclusive. So here I'm indexing by integers. So hopefully here, at this point, I know that this is time, this is probably, I think, latitude, and this is longitude. If I use this, then it's perhaps a bit more understandable. I mean, this is some time that I want, this is some latitude range, and this is some longitude. So it also works. You might wonder whether this will return a copy or a view. A general rule is that a copy will be returned if you use something like fancy indexing, which means that whatever you're trying to get is not representable by integers or slices. Otherwise, it should be a view. That also has implications for assignment. Now, if we don't want to deal with trying to remember where our dimensions are and what is their order, then we could specify the names to the values we're trying to index by actually giving a dictionary to the get item operator, and it also works for the location accessor. And this can also be used for assignment, but it's not exactly convenient. So that's why there are methods called isel and cell, which are for integer and label-based slicing and selecting respectively. But obviously, because these are method calls, they can't be used for assignment on the left side of an equal sign. Hopefully in the future, if this Python enhancement proposal gets through, we'll be able to write something like this, where you would specify the dimension, which would essentially be a short form for this here. Until then, if we use calls like this, we unfortunately have to specify a slice with a true slice object, because this will not be a valid syntax with a column anymore. But on the other hand, at least it works also for data sets. And there's also a thing called vectorized indexing, which enables very interesting tricks, but I won't cover that. You can look into documentation if you're interested. And so the equivalent of specifying something like this with the location accessor based on positions would be done like this with named dimensions. And you see that I don't really have to think about what is the order of the dimensions. And in my opinion, it's a lot more readable. And that's why I actually use it whenever I can, unless I'm very, very lazy, or if it's only 1D and then loc accessor is unambiguous. Of course, we also have nearest neighbor lookups. So the cell method has an optional method where you can say whether you want the nearest one, or the forward fill, or the back fill closest value. You could also specify a tolerance so that you don't get too far matches and you get a key if it's too far. So even though I'm specifying I want a latitude of 75.5 degrees and there's only 75 degrees available, I get the one that is pretty close. There's similar plot accessors you would find with Pandas data frames. There's this sort of a magic plot accessor, you can even call it, and it calls the appropriate method based on what's the dimensionality of the data array you're trying to pass. So if I do this, then since air is 3D, that means it's more than 2D, it can't really plot it in any obvious way. So it's going to just give me a histogram of all the values. And you see that it actually somehow found the names of the units and the description of the signal. And that's because if the description of the units attributes are available for a data array or a coordinate data array, it will use them for the labels. And if I select just some time slice, so now we'll be 2D, then it will automatically plot it with a P color mesh wrapper. And again, you see that it found all the various names of the axes and so on, and nicely labeled the time. So we can then, of course, modify this plot with typical matplotlib calls, although you have to remember that you should modify the plot after you do the Xarray calls because they modify the titles themselves, so otherwise they might override whatever you change. There's some more advanced features. For example, if you can use faceting with even 3D arrays, and if you want to be sure that the x-axis corresponds to longitude, then you just say so, and it handles all of the orienting and on its own. So here you see that I took 4 time slices, and I said that I want them that I want the time dimension wrapped in columns with a faceted grid. This is similar to what you might know from Seaborn. Another useful thing is that I could plot a 2D array as a group of 1D lines. So here I select will be just a 2D array, and then I say plot it as a line. I can use matplotlib pyplot style formatting, format strings, and I just say that on the x-axis I want the time dimension with some alpha value and some sizing of the figure, and it automatically adds this legend and labels the various time traces. When you want to work in a more interactive way with plotting, I personally prefer the hvplot accessor, which is provided by the hvplot project, which in turn wraps HoloViews, which in turn wrap bokeh. So that gives you a much nicer interface because now you get a nice tooltip and you can zoom in, as you might know from bokeh and so on. And you get also a nice slider. So it's very convenient. On the other hand, it's not so easy to use when you want to save an actual figure. As I've already said before, most NumPy-like methods, where you would need to specify an axis, then you can usually, if you use a data array method, then you can specify a dim name instead. You can still specify an axis number if you want to. By default, almost all of these methods skip not a number values. You can control that by a skip NA argument, as you might do in Pandas. And the attributes that you might have assigned are quite often dropped by these methods because in theory, if you do some transformation on a matrix, it's a different matrix, so you shouldn't keep keeping the attributes anymore. So here you see that I just specify, give me the mean over the longitude dimension, and that's it. Here I'm actually assigning the result back into the data set, so you can use a data set as sort of a data namespace so that you keep all your data on the same coordinates. So it's pretty convenient if you want to then later slice all the data variables at once. And you see that that we reduced the longitude dimension away. And here we can also see that this variable appeared here since we assigned it there. Now, if you want to wrap some other NumPy methods, most NumPy functions, especially ufuncs, which do respect the array interface, they will correctly wrap the result in a data array object again and add some metadata. But if you don't encounter a function that doesn't actually do that, then you might have to use the apply ufunc function, which I'll show later. And sometimes you might get away with just getting the axis number from this helper method, but then it doesn't wrap it if you just give it the raw NumPy data. So whenever possible, try to use this helper function, which is much more general and much more robust. Of course, arithmetic operations, which are essentially ufuncs as well, they, as I said, they handle reshaping and aligning to an inner join of coordinates. by default, it does an inner join of coordinates. You can configure that by the set options method. So here, if I calculate the square root function of the means, and then I select just 3 latitudes, then if I subtract that, this array, which is only 3 latitudes now from the full array, then you see that it has only 3 latitude, just 3 latitude parts or coordinates. And it handles all of the reshaping and aligning, because of course RT has many more latitude labels and positions. So it handles all of that automatically, and I don't even have to think what is the order of these dimensions. It's just all done automatically. There's a big fat warning. If I now try to assign this sort of smaller array to this whole data set, then it will actually align it to the outer join of all coordinates of members. So if I run this, you'll see that suddenly there's a lot of nan values because it tries to align it with the other ones. So that's something to remember, especially when you have very sparse variables, that if you sort of merge them into a data set with some variables which might be larger, smaller, or positioned at different coordinates, you might get a lot of nan values, and that might occupy a lot of memory. So that's something to remember. Of course, this is a mapping, so we can easily fix it like this. And now let's get to the wrapping. Whenever you want to wrap a ufunc-like function, or even a generalized ufunc function, that's a ufunc that can return more results, then it's best to use this apply ufunc helper. What this does is that it prepares the data within any data Xarray container you pass, including a data set, because it wraps over all the possible data arrays, and it prepares the ND arrays from these variables, or perhaps Dask chunks, and it moves something called core dimensions to be last. So it transposes the dimensions so that the dimensions that you select as core are last, and they are not broadcast. And it handles all the reshaping and aligning of the other dimensions and the broadcasting. And then it applies this function to any arrays or possibly chunks. And it's expected to apply only on core dimensions in a sort of an axis equals -1 fashion, or perhaps to all of the dimensions at once. If it's not a function that is vectorized on its own, like a typical ufunc, it will wrap it by NumPy vectorize if you tell it to. It can even parallelize over Dask chunks if you give it a Dask array, and it's great if you combine it with a NumPy geovectorized JIT function. And then it wraps the results, several results, in Xarray containers again. So for instance, if I want to apply the Sobel filter from Scipy ND image library, then I just apply this function. Let's say I can apply it to the whole data set. And all I need to say is that I want it to be applied along the latitude dimension. So I'll say the latitude dimension is the core dimension. Here it's actually the syntax is a little strange because you have to give a list of lists of core dimensions for each of the inputs. So since I'm giving only one input, it's actually a list of just one list. And then on the result, because we didn't reduce the dimension, it's still there, then that core dimension is still present. So we have to specify that as well so that I can wrap it correctly. And then we just have to specify that the keyword arguments passed to this function or method or whatever does get that it should apply along the last dimension, the last axis, since the core dimension will be moved there. Many functions have this as a default, but if you're not sure, then you should check the documentation. So here you see that I'm applying to the whole data set, so I'll get a new data set. And then if I just get the error variable from that data set and plot it, then you see that it indeed was applied. So there are many libraries that have used this to make some functionality from other libraries available. I've contributed, and some of my colleagues, to, for instance, the Scipy library, which provides some common Scipy wrappers for spectral analysis, filtering, integration, and so on. It's got some rudimentary documentation, although it's in kind of sort of an alpha stage. So here, for instance, I just import Scipy, and I can import the signal sub package, which contains the Savitsky-Golay filter. For those of you who don't know what a Savitsky-Golay filter is, it essentially runs along data, and it gives you the same result as if you sequentially fitted polynomials of a given order, and gives you either the value at the point at the center of that fit, or perhaps a derivative of that polynomial at that point. So here I just apply a Golay filter, and I just specify along which dimension. And I can even say that the width of the window will be specified in the units of that dimension. So I'm here giving a window of 30 longitudes. And you see that it essentially took the derivative through a second order polynomial. Another useful library that we've developed with some of our colleagues is one that wraps Scipy stats and also Arch, which we use for bootstrapping. Probably will merge it in the future into Xarray Scipy, at least the Scipy stats part. And it's even got a nifty feature where you can have sort of virtual sample counts via a Dask tree, and then you apply operations to these virtual samples, and you sample these, you actually create real samples only at the end when you have a real Dask tree ready. That's even more alpha stage. But anyways, it's quite usable. So if we import its stats, then if we, let's say, have an array of means and standard deviations, here we have just a 0D, just a scalar value. Then we can apply it to some stats methods, for example, to create random values. And it handles all of the broadcasting with sample sizes and so on automatically through the apply ufunc helper. And especially if you've tried to do it on your own, you might know that it's not that easy with stats because it's got this strange convention. And this creates a data array which has a sample dimension along which you could then perform some averaging or whatever you want to do. So for instance, you might apply some nonlinear operations, and then you might average over the sample dimension. And again, you get some result. And finally, we're getting to the last part, Dask chunking. For those of you who don't know what Dask is, it essentially splits an array into memory chunks, and then any operations that are supported are applied to each chunk in a parallel, either, let's say, through threads or in a multi-processing way, or perhaps in a cluster. And Xarray exposes the Dask interface, so you can easily create a Dask. You can easily turn a Dask array, you can easily turn a data array with just an ND array into something that has a Dask array underneath in its data attribute, simply by calling the chunk method, which just expects a mapping from dimension into how large you want the chunk size to be in that dimension. And most of the methods and operations that you might apply to a simple data array will work, most of them, and they will be simply added to Dask tree. And then once you want to evaluate the Dask tree, you just call the compute method. So to give you an example, here I'm importing the progress bar just to later on show you that some things might be a bit slower. So let's say I have this air temperature array, and I chunk it in the time dimension into blocks that have 50 elements in time dimension. And it even shows us this nice HTML representation of the Dask array. So you see that even though it has something like 16 megabytes, then each chunk has only several hundred kilobytes now because it's split into these chunks. And any operations that we might apply will be performed in parallel on each chunk and then added together. So for instance, if we apply the mean over time, then it will calculate the mean over each of these chunks. This actually isn't a very efficient example to perform a mean over chunk dimension, but it doesn't matter. And then if you call the compute function, it will actually then will it calculate the result. So in this case, it was very fast because obviously this is a very simple operation. But now let's get to the cherry on top. And that is that if you combine broadcasting with Dask, you can get very cheap, parallelized, out-of-memory for loops. For instance, you typically might have the problem that you want to calculate for each time the percentage of times that the temperature was warmer at that given time. So that would mean that you would have to run a 4 cycle if you want that to fit into memory, because that is a sort of a n by n problem. And then for each time you would calculate this and store it and then concatenate it into a new array and so on. But a sort of solution for lazy people like me is that you create sort of a copy or rather the view of the array, and you give it a different dimension called, let's say, time2, and then you broadcast it a lot against the original array, but you have to remember to chunk it, otherwise your memory usage will explode. And because of the broadcasting, you'll get this outer product. So let's see what happens. If I rename the time dimension to time2, I will get a new data array, which is just a view of data in this one, but it has a different dimension. And now if I apply this operation, I just ask, well, remember, this one is the one with the chunks. This already gets chunked. And if I say, well, where is this value larger than this value element-wise, then this will actually create a chunked data array, which you see that if I really did it in true memory space, it would have something over 11 gigabytes. But because I chunked it, then each chunk has only around 200 megabytes. So it's still, if each operation, if any operations are computed only on each chunk, it will still fit into my memory. And Dask will make sure that I don't overcommit my memory. So here, then I just calculate the mean over this time2 dimension and compute it. So now this will take a bit more longer, and we can see that my threads are very active. Though my memory usage isn't that bad, so that seems to be done. And here we have a result. So you see, I didn't have to write one for cycle. I just used the beauty of broadcasting and outer products. And because we use dimensional metadata, I didn't even have to think whether there's an outer product or anything like that. It just happens automatically. So I didn't cover many other things, but I just can't take the whole night of your time. But most of the other things that I didn't cover are quite similar with pandas or are very domain specific. So all I can say, just go check out the docs. They are really great. Just to give you an idea, all of the documentation has many examples and is very well written. Most of it is code that you can directly copy, paste, and play around with it. And now to summarize, why you might want to use Xarray, you might ask yourself. So for me personally, the most important thing is that it has explicit dimensions metadata. So in my opinion, that leads to more readable and safer code. And it also gives you a very convenient handle on all the broadcasting magic and more complicated function application. And the great thing is that it simply generalizes tried and trusted NumPy and Pandas API and Dask API and beyond. So it's not just a new kid on the block. It actually uses some things that have some proven technologies. And yet it's a very versatile and quite universal thing in terms of all the data structures, which means that it kind of leads to standardization. So all of the extensions that I have developed or other people have developed, I can use them in any context where I can get the data into Xarray containers, which means I can transfer any code that I have, which is written for Xarrays, to any other field or any other problem that I might encounter. And there's a lot of these extensions and additions. There's, of course, a lot of them for geosciences, since this package comes from that domain, but there's even applications for machine learning. For example, there's Arvis library, which is used for Bayesian models or their analysis, and many other domains. And it has even expired some C APIs. So that's it from me. Thank you for your attention. And I'm looking forward to your questions. And I hope that I've at least given you some reason to think that Xarray is indeed more than just pandas in multiple dimensions. Thank you.
Thank you very much, Ondřej. There are 4 questions on Slido, so let's go really quickly through them because it's getting late. So first of them is, do you know how much the performance overhead is compared to pure NumPy, whether it is significant when compared to pure NumPy?
Of course, there is some overhead because you are working with some Python objects, though since a few versions ago, they have defined slots for these objects. So it doesn't actually occupy that much dynamic memory anymore. And it's a bit faster, but yes, there is some overhead. So definitely it does make sense if your data is at least, I don't know, a few 100 megabytes or so, if you want to really be faster. I mean, it's not actually about speed. It's all about convenience of usage, which in terms of development can turn out to be even more important. So it's not really about speed. It's about how convenient it is to use and how much time you'll spend on developing and working with all the functions.
Thank you. So second question was about executing the cells in the slide. Someone is asking how you do it. I mean, just directly in the presentation.
Right. So this is essentially just a Jupyter notebook, and it's available on a small repository. And I just used something called the Rise extension for Jupyter Notebook, which essentially just activates the reveal.js slides for the notebook while the notebook is live. And also I used the split cell extension, which makes it possible to have these cells side by side. And I had to add some CSS overrides so that the HTML output would display correctly. So that's how.
Okay, another question. Would you comment on Xarray compatibility with scikit-learn and Cython? If you know something.
So in terms of scikit-learn, I know that there are already some libraries which do provide some interface, and essentially you can easily move from a data array to pandas. So you can easily convert it back to a data frame if you have something that wants to eat a data frame. So it's not that hard to use. And in terms of Cython, I don't think there's any direct compatibility, but it's pure Python and it does use slots, so it should be pretty easy to use in Cython, since it's just using NumPy. If you use mostly things that are supported by Cython, as in NumPy and pandas, then it should work.
Okay, and the last question is about the attribute cohorts, which is the coordinates, whether it can be something else than just the pandas index, such as a, in quotes, duck index.
I don't think so. I don't think that they have done much work on supporting that. I guess it kind of might work, because they do base most of their usage on duck typing most things, so it might work, but I don't think that's something they are planning on supporting directly.